So here is the question number 31. The magnetic field in a plane electromagnetic wave is given by vector B equals 2 into 10 to the power minus 7 sine 0.5 into 10 cube x plus 1.5 into 10 to the power 11 t j cap. The electric field is given by what? Now we have to get the equation for electric field. We know a plane electromagnetic wave propagating in a positive x direction. The magnetic field equation can be given by B equals B naught sine omega t minus of kx. After comparing this equation with the given equation, we can say that the wave is traveling along negative of x direction. Plane electromagnetic wave is propagating along negative x direction minus I cap. The equation for electric field E may be given by E naught sine of 0.5 into 10 cube x plus 1.5 into 10 to the power 11 t. Now, in order to calculate E naught, we know very well that the ratio of E naught and B naught will be the speed of electromagnetic wave, and the speed of electromagnetic wave can be further written by omega divided by k. Taking the omega from here, which is 1.5 into 10 to the power 11, taking the k from equation, that is 0.5 into 10 to the power 3, we get E naught upon B, that is equal to 3 into 10 to the power 8 meter per second. So from here we get E naught equals 60 Newton per Coulomb after putting the value of B naught. So E naught already obtained. Now let's get the direction of oscillation of electric field. The wave is propagating along minus I cap, and we know that the direction of wave propagation will be always perpendicular to vector B and vector E. So we can write here from that wave will always propagate perpendicular to propagation of electric field cross magnetic field. So here x cap is the direction of propagation of or oscillation of electric vector. So the magnetic vector here minus I cap equals x cap cross j cap. This j cap is for magnetic vector, this x cap for electric vector, and here is direction of propagation of wave. So after thinking, j cross k gets you plus I. Once again, j cross k gets you plus I. Then k cross j gets you minus I. So here we can write x cap equals k cap. It means the electric field is oscillating along k cap. So the answer will be option number 1. So final electric field vector can be given by 60 volt per meter or Newton per Coulomb sine in bracket 0.5 into 10 to the power 3x plus 1.5 into 10 to the power 11 t k cap. So this is the electric field given. Now let us proceed to the next question, that is question number 32. Instantaneous displacement current 2 ampere in the space between parallel plate of 4 microfarad capacitor can be established by changing the potential difference at the rate of what? We know very well that the displacement current is given by epsilon naught d electric flux of dt, rate of change of electric flux, which can be further written epsilon naught. Electric flux can be written as electric field multiplied by area of the plate. Area of plate will always be constant, comes out of differential, gets you epsilon naught A. Electric field is equal to V by D, where V is the potential difference and D is the separation between the plates. So we can write d by dt of V by D. Again, the plate difference or plate spacing will always be constant. So D comes out and gets you epsilon naught A by D into dV by dt. Now dV by dt is the rate of potential difference. Epsilon naught A upon D is the capacitance of the capacitor and ID is displacement current. Putting the values, we get 2 equals C, that is 4 into 10 to the power minus 6 into dV by dt, and after solving we get dV by dt as 5 into 10 to the power 5 volt per second, time rate of potential difference. We will go with option number 1. Now let us proceed to the next question. So here is question number 33. There is a current carrying straight wire of infinite length having current 5 ampere. If the square loop of side 10 cm is kept coplanar with the wire as shown in figure, the magnetic flux through the square loop will be what? Now, here we have to calculate the magnetic flux bounded with this square loop. But this square loop is kept in a region of varying magnetic field. If you move toward wire from the square loop, then the magnetic field is changing. So, in order to calculate the total flux, let us consider an elemental thickness of the square dx at a distance x from the current carrying wire. The magnetic field along or at every point of this dx can be written simply mu naught I upon 2 pi x. A small area of this element will be given by length, that is 10 of course in centimeter. So in meter you have to divide by 100, 10 by 100, multiply it by its width, that is dx. So ultimately the small elemental flux bonded with this small element will be given by B into A or B into dA, that is mu naught I upon 2 pi x dA, that is 1 by 10 into dx. Now the net flux bounded with the square will be given by integration of d phi, that is integration of mu naught I upon 2 pi x multiplied by 10 times dx, where the limit of x in order to cover complete square will be from 10 centimeter to 20 centimeter. Put the constant outside of the integration, you will get mu naught, that is 4 pi into 10 to the power minus 7 multiplied by electric current, that is 5 ampere, divided by 2 into 10, that is 20 into pi, and rest of the expression will be within the integration, and integration of 1 by x is given by log x, limit 10 to 20. Now 4 pi into 10 power minus 7, pi cancel out, it gets you 4 pi 20 into 10 to the power minus 7 whole divided by 20. Putting the limits, you will get log 20 minus log 10. Log 20 minus log 10. You know that log A minus log B equals log A by B. So 20 upon 10 gets you directly log 2. So ultimately your answer, the total magnetic flux bounded with this square will be 10 to the power minus 7 log 2 Weber. So that's why we will go with option number 4, which is absolutely correct. Now let us proceed to the next question, that is question number 34. Now here is question number 34. There is a conducting rod of length 2L that lies along x-axis from x equals minus L to plus L. If rod moves with velocity v equals v naught I cap and in the magnetic field B equals B naught K cap, then induced EMF between the ends of rod is. Now here we can say that the rod is moving along its length, and when a conducting rod moves along its length, then no EMF will be induced. So here no EMF will be induced as rod is moving along its length. we will go with option number 1. Now let us proceed to the next question. That is question number 35. Which of the following statement is correct about induced electric field? So here are some statements, some options regarding the induced electric field, not the general electric field, and we have to check which one is correct. Here we do not have to check incorrect. Here we have to find the correct option. So first, the field is produced by variation of magnetic field with respect to space. No. Induced electric field is obtained by the time varying magnetic field. So first option is wrong and we have to pick up the right option. Field is conservative in nature. No, induced electric field are non-conservative in nature. The electric field which we have covered electrostatic chapter is conservative in nature, but here the induced electric field is non-conservative in nature. So that's why option number 2 is also wrong. We cannot define potential corresponding to this field. Yeah, this option is absolutely correct. The potential cannot be defined for the induced electric field. So this is correct option. Now fourth option. The line of induced electric field are not closed curve. No, the induced electric field lines always form a closed curve. So this option is also wrong. So that's why we will proceed with option number 3. Now let us proceed to the next question. That is question number 36.